Hi class, and welcome to our next lesson on 9.3, which is graphing rational functions. We've been doing a lot of work with simplifying rational expressions. Now we're going to have an equal sign in there, so we're dealing with rational equations, and we're going to be graphing them in this section. But first, let's talk about a couple different terminology aspects. With rational functions, they're always undefined when the denominator is 0. So we can't even graph a rational function when the denominator is 0. So class, on this first one here, when does the denominator, x plus 3, when does it equal 0? Well, that is when x equals a negative 3. So we know that when x equals a negative 3, it makes a 0 in the denominator, and that can never ever happen, because we cannot divide by 0. That's one of our math rules. So on this one, we just know that x can be any number except for it cannot be a negative 3. That's what that symbol means right there. X cannot equal a negative 3. All you have to do is set your denominator equal to 0. On this second one, x cannot be two different numbers. If you put a 1 in here, 1 minus 1 is 0, and 0 times anything is still 0. So we know that x cannot equal 1, and the other one is x cannot equal a negative 4. Because if x was a negative 4, well, a negative 4 plus 4 is 0, and 0 times anything is 0, and you cannot divide by 0. That is a math rule. And then the last one here, x in the denominator, right here, we know that it cannot equal 0. So we know that x cannot equal 0 because that would make a 0 in the denominator. So bottom line, class, get this into your head. You can never divide by 0. For these rational graphs, we're going to be dealing with variables in the denominator, and that denominator rather, cannot equal 0. Alright, rational graphs. They may have breaks in continuity. That means that they are not always traceable without picking up your pencil. So we've done linear graphs. We never need to pick up our pencil. We can keep on going forever and ever and ever and ever, and we never need to pick up our pencil. The same thing with parabolas. When we have our quadratic graphs, we can trace this. Whoopsie. We can trace this forever and ever and ever, and we never ever have to pick up our pencil. We can just keep on going up and up and up and up, and we would never ever ever have to pick up our pencil. Not so with rational graphs. With rational graphs, there are times where here might be our xy coordinate grid, where we have something that looks like this. Right here, you have to pick up your pencil and start up again right over here. So that's the bottom line with rational graphs. We might have there will be times where we have to trace them, and we have to pick up our pencil in order to do so. There's going to be some vertical asymptotes. What this means, class, is that a vertical asymptote is a line that the function approaches infinitely. These are determined by the factors that remain after simplifying the function. I'll talk more about that when we get into our graphs. So not only vertical asymptotes, there might also be horizontal asymptotes as well. Those are lines that the graph of the function whose end value approaches a certain y value. These are determined by looking at the table on your graphing calculator. So our rational graphs might be something that looks like this. Here comes my function. It's going to start coming up, and it's going to go up and up and up infinitely right here. However, this might be a vertical asymptote right here. This blue line right here is a line that my graph approaches. It gets closer and closer and closer to, but it never ever touches. It approaches it infinitely. It infinitely gets closer to it, but it never quite touches it. The same thing is true coming down on this side. It might get closer and closer and closer to it, but it never actually touches it. That is called a vertical asymptote. And the same thing with a horizontal asymptote, just going from left to right. And the last thing, with these rational graphs, there are times where we might have some removable discontinuity. Another word for this is a hole in the graph. The definition, there is a hole in the graph. That is determined by the factors that were canceled out when simplifying the function. So you might have a function that looks like this. Something that looks like this, and then something that looks like this over on this side, except right here, there might be a hole in the graph. And then it continues to go on this way. So once again, there's a break in continuity. I have to lift up my pencil right here to start tracing now on this side. That's also what it means by breaks in continuity. And that is a hole in the function or a removable discontinuity. So, knowing all those things now, the directions here are determine the equations of any vertical asymptotes and the values of x for any holes in the graph of each rational function. Now class, both vertical asymptotes and holes are found after simplifying your equation. Where does it say that over here? Right here. These are determined by the factors that remain after simplifying the function. So the first thing that we have to do is we have to simplify this function. So we're going to use our work from the first half of Chapter 9. Let's factor this, and let's factor this. So now we have y equals x minus 1 times x plus 1 divided by x minus 3, x minus 5 times x minus 1. So now our simplified equation, we can now cancel common factors or reduce them, x minus 1 and x minus 1, to make y equals x plus 1 divided by x minus 5. So this is our simplified equation. Now from this, we want to determine any vertical asymptotes. So a vertical asymptote, that is going to be when my denominator equals 0. When does x minus 5 equal a 0? Hopefully you can see quite simply that that is when x equals a positive 5. So I know that I have a vertical asymptote at x equals 5. The other one that I have to find is I have to find if there are any holes in the graph. Holes in the graph are determined, removable discontinuity, by the factors that were canceled when simplifying the function. So what factor was canceled when we simplified this function? The x minus 1 factor was canceled. So in the same way, when does x minus 1 equal 0? Well, that's when x equals a positive 1. So that's going to be my hole or my removable discontinuity. It is when x equals a positive 1. So I have a vertical asymptote at x equals 5, and I have a removable discontinuity at x equals 1. This is your answer for problem number 1a. Why don't you guys try problem number 1b on your own? First you simplified the function, cross off any common terms, any common factors, and then state your removable discontinuity and your vertical asymptote. Pause the video and try that on your own. When you simplified, you should have got y equals x minus 2 times x plus 2 divided by x plus 3 times x plus 2. So your simplified equation, after you reduce the x plus 2's, you now have y equals x minus 2 divided by x plus 3. So your vertical asymptote is when x equals a negative 3. And then your removable discontinuity, that hole in the graph, is that canceled factor, which is x equals a negative 2. Vertical asymptote at x equals a negative 3, and removable discontinuity at x equals a negative 2. Make sure you ask me questions tomorrow if you have them. Those two terms are big, vertical asymptotes and removable discontinuities. Be sure to ask me questions if there's something that you don't understand about that.